Welcome to the sixth Millennium Problem Talk. I don't have to tell you who our speaker tonight is. He grew up in Chicago, did his undergraduate work at Harvard, and got his PhD at Berkeley under Iz Singer. After postdoc years at MIT in Chicago, Fried came to UT in 1989 and is now a professor of math here with a deep interest in physics. He's done research in geometry, analysis, quantum field theory, and string theory. In recognition of his achievements, he's been awarded several fellowships, NSF postdoc, and a PYI, that's a Presidential Young Investigator Award. Fried has great energy. He's written two books, one with Karen Uhlenbeck, and over 40 research papers. Besides that, he's edited several books and journals, helped organize more than 10 conferences, and given more than 40 invited talks. The year he came to physics, to UT, his interest in physics paid a big dividend. He met and soon married Sonia Paban, a young Spanish physicist who was here on a Fulbright scholarship and is now an assistant professor in physics at UT. Most of our speakers have been musicians, and Fried has been amateur musicians. That's what I had prepared, amateur musicians. And Fried is no exception. But I just learned he's not an amateur. He's a member of the Musicians Union. He's played with the Berkeley Symphony Orchestra of the town of Berkeley, and he's played with the Austin Opera. He's played at Tanglewood, and he actually sort of followed the advice of Karen Uhlenbeck and his PhD supervisor, Iz Singer, in turning down an audition with the Jerusalem Symphony Orchestra. But I think he regrets that. I'm not sure that that was good advice to follow, but we'll never know. Anyway, I should mention that his instrument is the trombone. For exercise, he likes tennis and jogging and hiking. But he tells me that his two sons now leave him little time for any of these avocations or other professions. Before the talk, and I, and indeed almost all of us so-called experts, I want to say that we think Dan Fried has the most difficult problem to explain, the Hodge Conjecture. Our first speaker in the series, Cameron Gordon, could show pictures and talk about deformations to explain the Poincare conjecture. Our second speaker, Fernando Villegas, could discuss perfect squares and solutions to equations in whole numbers and integers to give an idea of the conjecture of Birch and Swinnerton Dyer. Lorenzo Sedun's problem, the Yang-Mills and the mass gap, had something at least to do with the real world. And to illustrate P and NP problems, Vijaya Ramachandra could discuss factoring large whole numbers or finding the shortest route for a traveling salesman. Louis Caffarelli's problem, the Navier-Stokes equation, has to do with the flow of an incompressible fluid like olive oil. And next week, and remember, the next talk, the last of the series, is 1 week from today, not 2 weeks. Next week, to explain the Riemann hypothesis to us, Jeff Waller will be able to refer to points in the plane and prime numbers to get the idea across. But I cannot imagine how tonight's problem, the Hodge conjecture, can be explained to non-experts. So I'd better shut up and learn how from Dan Fried. Take it.
Hello. All right. That was the most difficult part of the talk, I think. No, working this is the most difficult part, clearly. There we are. So, as John mentioned, I'm talking today about the Hodge conjecture. There you see Hodge, William Hodge, was a geometer. So this is definitely a talk in geometry. Hodge posed this problem in his 1950 address to the International Congress. That's a congress that happens every 4 years. And as you see from the quote there, that already in 1976, it was recognized that this is a central problem, and also predicted that we would have to wait many years for the answer, and that same prediction still seems to be true. I'll get this right. So it's a problem in geometry, but it stands really it involves many different currents in mathematics, from geometry, from algebra, from calculus, and several directions. So I'm afraid there is a lot to explain, and I'll try to emphasize the following themes. That in geometry, we study many different kinds of spaces. So we'll see many different kinds of spaces, and when I say abstract spaces, I mean that it's not the space of the real world, but they're geometric spaces of our imagination, and as we start to study them, more and more spaces will appear. And inside those spaces, we study different kinds of shapes, and depending on what kind of geometry, we study different kinds of shapes. And so I'll try to explain some of the different kinds of shapes we often call cycles. And as I said, there's going to be an interplay between geometry and algebra. And in fact, these three themes will be the subject of roughly the first half of the talk, where I'll try to develop the kind of spaces that the Hodge conjecture pertains to, the kinds of cycles in them. And there you'll see a lot of interplay between geometry and algebra. We'll then have to bring in some topology, as in the first lecture in this series, to explain some more new shapes that we see inside these spaces. And finally, to explain really what Hodge's conjecture is, we'll have to bring in some calculus. But let's start way at the beginning with the Greek geometers. So that's the geometry that I think is common ground for most of us. And here we'll discuss the plane. You see this yellow plane. That's the Euclidean plane. So you can picture it as the surface of a table, except if we're on a table, or a little ant going on the table, we'll of course run off the end. Whereas this plane, we can keep going and going. Despite the picture, it goes infinitely far. So you can walk infinitely far in any direction. And the shapes we'll start with are the simple ones, just points. You see 2 points there, and lines. You see 2 lines there. And while, as befits the Greek culture, all the symmetry, we have beautiful symmetry with points and lines. And we have the following 2 basic principles of Euclidean geometry. The first one is that any 2 points determine a unique line. Through any 2 distinct points, you have a unique line. And of course, any 2 lines intersect in a unique point. So we have this beautiful sort of symmetry between points and lines in classical Greek geometry. Not really. Because, unfortunately, we have parallel lines. And in fact, this was the postulate that gave everybody fits for years. Namely, there are lines which don't intersect in this plane. So if we have parallel lines, they just keep on going in the same direction. They keep going forever. As I said, this plane goes forever. and they never meet. So that point P with a question mark is not, there's no such point. So we'll take as our first problem to try to approach the Hodge conjecture is to find a new space somehow related to the plane where we fix up this deficit, where we fix this deficit that parallel lines don't meet. We'll try to somehow arrange that every two lines meet in one point. And to warm you up to that, we're going to think about the first of those postulates, which says that any 2 points determine a unique line. And let's ask a question that definitely is not part of Euclidean geometry, which is how many lines does 1 point determine? Well, if I just have a single point and ask how many lines pass through that point, well, you see there are lots of lines. And we'd have trouble counting them. It's not a number we can count. We might even say it's uncountable. So it would be better then to ask a different version of that question, which is what does the space of all those lines look like? So what I'm going to try to do is make a new space where the points of my new space correspond to lines through that point O. So what we're going to do is introduce, as I say, a reference line. And we're going to think of measuring lines through that point relative to this reference line. And the way we're going to measure it is by an angle. So this line is at 0 degrees. And we're going to just plot on this blue line here, we're going to plot the different angles. Now, you're used to that kind of representation. I mean, when you drive in a car, for example, you have there your Rand-McNally map or atlas. And a point on that map does not represent a point on that map. It represents some place on the Earth. The map doesn't look like the Earth at all. But anyway, that map is what we use to navigate around the Earth. So you see a point that says Peoria. It doesn't look like Peoria. You have a very different image in your mind. So here we have this point, and the image in your mind is this line that goes through there. And the point's labeled by 0, and that label is going to tell you the angle. So for example, we can bring in a point at 60 degrees, and that will correspond to the point 60, which lies there. We can bring in the 120, that line at 120 degrees, that corresponds to that point. So you see each point on this line, each angle there corresponds to a line. Well, what happens when we get to 180? Well, at 180 degrees, we're back to our original line. So then we stop. So if we want a space where each point corresponds uniquely to a line, then we should take this interval, not an infinite line, but just this finite interval, where I go from 0 to 180. Except we have that at the two ends, they represent the same line. So what we should really do is take the two ends of our line and identify them, hook them together. So as if I took a piece of string and identified the two lines. So of course, what shape do I get when I do that? Well, I get a circle. So the space of lines through any particular point, that seems to look like a circle. Well, let me tell you that again in a few other different ways. So instead of introducing this reference line and measuring angles, let me now instead introduce this sort of circle here. And what I'm going to do is intersect every line through the point O with that circle. And on that circle, I'll measure in terms of degrees. So for example, this purple line intersects at 0 and 180 degrees. So these two opposite points on this blue circle represent the same line. And similarly, if we bring in this line at 60 degrees, these two opposite points, 60 and 240, I hope I did the arithmetic right, those represent the same line over here. And then our friend at 120 represents that line. And so we see we can think of this space of line as being the points on this circle, but with the antipodal points identified. That's the 360-degree circle. Well, again, this pair of points can correspond to a single point, and so to speak, a single point on a circle half the size. That was the circle before. So 1 point here can correspond to 2 points here. That corresponds to that line. Okay? All right, here's yet another construction. So for this construction, what I'm going to introduce is, again, an auxiliary line, this purple line, but it doesn't now pass through the point O. Okay? So for each line through O, then, what we have is that each line through O intersects that purple line in a point. So if I have a point on this purple line, I can take the unique line given by that postulate between that red point on the line and the white point, which is the origin. So here we have another line, and it corresponds there. Well, there's one problem with that, which is that the line which is parallel to my reference line doesn't intersect it. So I've managed to account for every line through O with this purple line, except for the one that's parallel. You see that point of intersection, as we go closer and closer to parallel, that point keeps going out on that purple line. So that's really the problem with parallel lines. right, this purple line and this dotted line are parallel, is that what should have been the point of intersection is going further and further out. And again, this Euclidean plane, we can walk as far as we want. Okay, so how should we rectify this situation? Well, we'll introduce some points way out on this line. We'll call those infinity. So we have one, so to speak, to the right, one, so to speak, to the left. But going to the right or going to the left is the same, because if I rotate this line a little bit further clockwise, then the intersection point will be way out to the left. If I rotate it a little bit counterclockwise, the intersection point will be out to the right. So in this space of lines, infinity to the right, points far out to the right are close to points far out to the left. So we want, however we're representing the space of lines, we want close points to correspond to lines which are close. So again, we have this picture of this line where we identify these 2 points. And so we'll see a circle that way. Well, here's an analytic way to see the space. And so we introduce coordinates, and the man that did that is Descartes. We know about the Cartesian coordinate system. And so if we have a point in our friend the Euclidean plane, that's still our space, this yellow box there, then a point is represented by a pair of real numbers. If I want to locate a point on this purple axis, the horizontal axis, I just need to give a single real number, which tells me the distance from O to that point. If it's negative, I go to the left. If it's positive, I go to the right. And so if I want a point in the plane, I give a pair of numbers. They tell me the distance from each of these axes. Okay, so that's an analytic way in which we in which we can study geometry by writing formulas. I mean, it's a very important idea, of course, in the development of mathematics. So what does a line look like? How can I characterize the real numbers x and y, which lie on a line through O? Well, it's the set of real numbers, x and y, that satisfy an equation like this. That's a linear equation. And so you see the line, then, is given by this pair of numbers, a and b. So if you give me 2 real numbers, a and b, then I'll be able to draw that line. It's all solutions to that equation. Well, what happens if I multiply a and b by a number like 2? So I ask that ax plus by is 0. That's my first line. And my second line is twice a times x plus twice a times plus twice b times y equals 0. Or here I've written the number lambda in general. Well, the solutions are the same. If x and y satisfy this equation, just multiply both sides by lambda, they'll satisfy this equation. So that means that the pair AB and the pair 2a and 2b and 3a and 3b and so on, they all determine the same line. So this space of lines is given by pairs of numbers. They can't both be 0, or we don't get anything. But we only know this pair of numbers up to this kind of scaling. Okay, so that's another sort of analytic way in which we represent this space of lines. So this space of lines is what we call RP1, the real projective line. You see, we started, one picture is we have this purple line, we call the affine line, and we've added this point at infinity, and that's called the projective line. So the space of lines, as I say, looks like a circle, and we have 3 descriptions. Our first description was in terms of these angles, right? They lie on this circle. The second was we have this line, and we've now added this point at infinity. And finally, our third description was an analytic one as pairs of numbers up to scaling. Okay? So that's our first new space. By asking questions about the Euclidean plane and just simple objects in them, points and lines, we're led suddenly to a space which looks like a circle. Okay, so that's how we can make new spaces, by asking such questions. All right, so now we come back to our problem, which is that lines in the Euclidean plane, parallel lines exist, they don't intersect. And so we want to somehow compactify, which means to add things in infinity. So I can't go off forever. We want to compactify so that the lines intersect in exactly one point. So here's the idea. We're going to add at infinity this whole circle. And that whole circle you should think of, oh my God. Okay. Keep that. Well, okay. That whole circle you're supposed to think of as the projective line at infinity. So try it once more. Okay. Well, okay. So 2 parallel lines will intersect at one point here. If they point in the same direction, remember that this circle is the circle of angles, right? So what we have is that if we have a line at a certain angle, it corresponds to one point at infinity. And all the lines at the same angle, in other words, all the parallel lines, pass through the same point at infinity. So that's the idea that we somehow want to add the angles in infinity and ask that lines at that angle pass through that point. So two lines at different angles will intersect at a point in the ordinary plane. That's what we had before. And two parallel lines will intersect in this extra projective line that we added in infinity. Now, that's not a very good picture in that I haven't tied together, so to speak, this blue circle and the yellow plane. Here's a different picture, which is analogous to our second model of the projective line, to show you how it looks. So take this Euclidean plane to be up here, and let's take a point not on it, call it O again, and let's look at the space of lines through O, where now in this whole space I'm looking in our ordinary three-dimensional space. So instead of the surface of a flat table, we're now looking inside three-dimensional space. So every line through this point will intersect this plane, and so each line corresponds to a point in the plane. Those are the points in the finite part of this, in the ordinary Euclidean plane. But the lines that don't intersect the plane are the lines through O which are parallel to this plane. In other words, they're the lines which lie in this blue plane down here, this parallel plane. So any line through O that's in this blue plane will not intersect this yellow plane. But if I tilt it off a little bit, it will. And where will it intersect this yellow plane? Well, if I just tilt a little bit, we're going to have to go way out to find that intersection point. So those will intersect at infinity. And what do we have in this plane? Well, we have all the lines through the point O in this plane. Well, that's our old friend at infinity here. That was the projective line we started with. So this green line, for example, that lives there, it's actually green, corresponds to that one point in infinity. Remember, these two opposite points, like 0 degrees and 180 degrees, correspond to the same point in that space of lines. Okay, we can also give a coordinate description of RP2 in terms of this space of lines. So that compactified plane is called the real projective plane. That's called RP2. The 2 up there refers to the dimension. So a plane, as I said, we need 2 numbers to navigate on the plane. A line, we just need 1 number. So that's called one-dimensional. The plane, we need 2 numbers. And if we think of it as this space of lines, then, as I said, this space of lines is given by a triple, x, y, z. If I have a triple where they're not all 0, then I can take the line through the point O and through this point x, y, z. But x, y, z will determine the same line if I multiply them all by a constant. So we could think, for example, of vectors, a vector that goes from 0 to here. So if you're familiar with displacement vectors, we can think of these as all the vectors which are multiples of each other. They lie there. And so having all the non-zero vectors in space up to this, where I identify ones which point in the same direction, that's this projective plane. Okay, so that's the description there. We have triples up to identifying by that scale. Well, this projective space is one of the non-Euclidean geometries, so we've skipped 2,000 years here. And that parallel postulate really caused fits, and many people tried to get around that. And there were other geometries developed in the beginning of the 19th century, mostly the hyperbolic geometry, Lobachevsky and Boyer and Gauss and so on. That was something new, where you actually had a geometry where there were points and lines and a point not on the line, and you found lines that didn't intersect at all and weren't parallel. You found lots of them. This projective geometry was around, but it was really Felix Klein who, at the end of the 19th century, sort of put all these geometries into one picture. Okay, so again, this real projective plane, it's a compactification, means we've added something so that we can't run off to infinity. And because we can't run off to infinity now, in the plane we have that any 2 lines intersect in a point. So now we understand points and lines in the plane. Well, that's not so interesting after a while, so we want to study more circles, more shapes, I mean. And in Euclidean geometry, we also have circles. So let's at least introduce circles. So we have points, lines, and circles. And we can ask again, focusing on this idea of intersection, how many points are there in the intersection of 2 circles? Okay, so here's our plane with 1 circle, and let's intersect with another circle, with a line first. So let's intersect a line and a circle. So here's a line which doesn't intersect the circle at all. Again, you should imagine this line and this plane is going on forever. But if they go on forever, they'll still never intersect the circle. You see, the circle doesn't go on forever. It just winds here. So if it's going to intersect, it has to intersect where we can see it in the picture. Not being able to see out here won't produce any intersection points. Well, if we move the line closer, we might get a line which actually only intersects the circle in 1 point. That's called the tangent line. Or we might get a line that intersects in 2 points. So we can have 0, 1, or 2 points of intersection. And if we ask the question about circles, we'll find the same thing. If we take two circles, they might not intersect at all. They might intersect in one point, or they might intersect in 2 points. Okay, so why does the number of intersection points vary? Well, to study that, one thing we can do is look in our Cartesian coordinates and try to write equations to see that. So if we write the equation for a circle with center at the origin, say of unit radius, then that's the equation x squared plus y squared minus 1 is equal to 0. So the set of points x and y, now they satisfy a quadratic equation. Quadratic means that we have second powers of x. Okay, the equation of a line in the plane looks like this. Before we didn't have the term c. That was set to 0. That was a line through the origin. But in general, we'll have the term c to represent a line through any point. So here, a, b, and c are some real numbers, which are the coefficients. So we have two equations in two unknowns. And how do we solve them? Well, we could, for example, in this equation, solve for y very easily, if b isn't 0. If it is 0, we have to solve for x. In any case, we can plug back into here, and we'll get a quadratic equation in a single variable. So let's say that that variable is x. We get an equation something like that. So that's a familiar quadratic equation, and everybody remembers the quadratic formula, which tells us how to solve it. Minus b plus, well. So, in fact, quadratic equations have either two solutions, one solution, or no solutions, which is what we saw geometrically when we intersected the point and the circle. And it depends on this quantity here, whether it's positive, equal to 0, or less than 0. Of course, you can just take a simple example. Take the equation x squared equals 1. Well, that has two solutions. X is plus 1 or minus 1. We can take x squared equals 0. That only has one solution, x equals 0. Or we could take x squared equals negative 1, and that doesn't have any solutions at all. Okay, so how do we rectify that? Well, we introduce a new number to solve the equation that I just said doesn't have any solutions. There is no real number whose square is negative 1, because anytime I multiply a number by itself, I get something which isn't negative. If the number was positive, it's positive. If the number is negative, I multiply two negatives, I again get a positive. So we'll just introduce a new number and call it I. That's called the complex numbers. So a complex number in general is a sum of a real number plus another real number times I. And then every quadratic equation actually has a solution inside the complex numbers. So we've eliminated this case of 0 solutions by introducing complex numbers. Well, most of them have two solutions, in fact, like that equation, but we still are left with that equation x squared equals 0. Introducing the complex numbers didn't eliminate the problem that we only have one solution for that. So what we do is give up and just change our terminology. It's a good strategy. And so we just say that that has two solutions. Those are the algebraists sitting in the front row, so you have to, all complaints should be addressed there. I didn't make this up. So this is what we call a double root, or we introduce the term multiplicity to mean that somehow that root appears twice. Okay. So in that way, every quadratic equation has exactly two solutions. And as long as we've gone from linear to quadratic equations, we may as well look at polynomials in general. So a polynomial is an expression like this. In one variable, it's a sum of terms. Each term has a power of x and perhaps a coefficient. So this polynomial has coefficients which are integers, 1, 4, and 3. And that's then a cubic equation, cubic meaning order 3. Here's a nth order equation where n could be any positive integer. For example, 4,976, whatever that is. So we could have polynomials of very high degree. But nevertheless, notice a polynomial is given by a finite amount of data. If we have an nth degree polynomial, we have n plus 1 numbers is what we need, and then we know the equation. Similarly, we could write polynomials in two variables. Remember, the equation for the circle is a quadratic equation in two variables, and we can write higher order polynomials in two variables. So here's a cubic in two variables. And if we stick to one variable for the moment, then there's a wonderful theorem, which is the fundamental theorem of algebra, although it's a theorem in topology, which says that every polynomial equation of degree n has exactly n solutions, where, again, we have this caveat that we sometimes have to count the same solution as being a double, triple, and so on. So once we know how to count, then any polynomial of degree n has n solutions. Okay. Well, now that that's helped us in algebra, and we saw those algebraic equations coming from our problem in geometry, then clearly to get those intersection points for those circles, we have to introduce those complex numbers into geometry. So how are we going to do that? Well, that's where having Descartes and these coordinates comes to the rescue, because you see in the real plane, this Euclidean plane, we have that every point corresponds to a pair of real numbers. So let's just invent a new space where the point corresponds to a pair of complex numbers. So that we'll call the complex plane. So clearly, when we have these missing points where the line doesn't intersect the circle, if we now allow our x and y to be complex and we write down our equation, we should get solutions. So what's a line in our complex Cartesian plane? Well, I've told you what a point is. A point is a pair of complex numbers, and so a line is the set of complex numbers that satisfies a linear equation. And now, in fact, we can allow the coefficients a, b, and c to be complex, as well as the solutions. And what's a circle? Well, that should be the set of points that satisfy that equation. Okay? And notice that a pair of complex numbers is really 4 real numbers, because each complex number is a pair of real numbers. And so we have 2 real numbers corresponding to the one complex number x, 2 real numbers corresponding to the one complex number y, and altogether 4 real numbers. So to navigate in this space, I need not 2 numbers, but 4 ordinary real numbers. So if we talk about a complex line, remember a line is parametrized by 1 point. So a complex line we can navigate by having a single complex number. And so what does that look like? Well, that's really a pair of real numbers. So a complex line looks like our old friend, the Euclidean plane. So as a space, it looks like the 2-dimensional Euclidean plane. But in complex terms, it's a line. And what does a complex plane look like? Well, that's a space where I navigate by having 4 real numbers. That's not something we can easily picture because the world around us has only 3 dimensions. So as I said, when we start to study geometry, we start to get into spaces that we don't necessarily navigate. Of course, we meet that in physics if we had time. But anyway, so now to review our Euclidean plane, we've evolved it in 2 different ways. One is that we added this infinity so that lines, there's the picture I wanted. So now you see these parallel lines both pass through that green point in infinity. So we rectified the problem with parallel lines. And then we added complex numbers so that, for example, the circle and a line will now always intersect in 2 points. 2 circles, incidentally, will always intersect in 4 points. Okay, so now we combine these and we make a hybrid form. And the hybrid form is to use complex numbers and also add points at infinity. So again, it's good that we have this algebraic model, because in our algebraic model, we can make complex points. We have an algebraic model with real numbers, and so now we can let these numbers be complex. So this complex projective plane, CP2, that's our ordinary Euclidean plane, but where we allow complex numbers and add something at infinity, we can represent that mathematically as triples of complex numbers, where I identify triples that correspond under scaling, and now the scaling is also by a complex number. Okay, so we've evolved our notion of space. Instead of the Euclidean plane now, we have CP2, this complex projective space. So that's our new arena for geometry, but it would be nice to have more interesting shapes inside there rather than points, lines, and circles. So what we can do is consider polynomial equations which are of higher degree. So I showed you that lines and circles satisfy polynomial equations. Why not just consider polynomial equations of higher degree? So for example, here's what solutions to an equation of degree 2 looks like in general. Our circle was one of those. Now what I'm showing you here is meant to represent something in CP2. But what I can show you on the screen is just something in the real Euclidean plane. So this CP2 is really some 4-dimensional space. It's hard for me to show you. What I'm just showing you is a meager slice of it and showing you how these shapes actually intersect this plane. So what do these shapes actually look like? Well, they're just bent version of lines. And remember, a line looks like a plane. So these shapes actually look like surfaces. So these shapes, although they look different in this slice, actually all just look like a sphere. And here you see some cubic equations. And so this is an equation of degree 3. And again, we see some different slices. But they all look like what's actually the surface of a donut. Okay. And in fact, if we take an equation of degree n and we want to intersect with a line, because we fixed up this problem of having these points go off to infinity by just adding points at infinity, so we can't get off of our space, and because we've made complex numbers so that our equations always have solutions, and because we've changed the way we count, then any degree n curve intersects a line in n points. So here we have a line, several lines, intersecting these curves. So for example, these curves have degree 2, as I say, so we expect the line to intersect in 2 points. And there you see the line intersects in 2 points. This curve has degree 3, and so the line intersects in 3 points. Well, here's some more lines. And that line also intersects that curve in 2 points. Remember, this is our funny way of counting. When we have this tangency, that's a double solution to that equation. Here again, we have 1 point here. That's a clean intersection. But here we have a double intersection because of the tangency. So again, we have 3 points that we can see. Well, here we have some lines where here we only have 1 point, whereas we expect 2. What happened to the other one? Well, this line is pointing in a certain direction, which runs along the axis of that parabola. And notice that the parabola is bending more and more towards its axis. So this parabola, as we get farther and farther out, is approaching the same angle as that line. And so those will meet, actually, at that point at infinity that we added. Before we even made complex numbers, we added that point. And similarly here, we have 2 points out of the 3 we expect. And again, you see that this thing is asymptotic to the direction of that line. So there's a 3rd point at infinity. But alas, we have this line which didn't intersect at all. Well, that has 2 intersection points, but they both lie in the complex numbers where we can't see them by this real plane. And similarly here, we expect 3. There's 1 we see in the real plane, but 2 which lie in the complexes. But if we work in this space, CP2, we always get those points. So these are simple examples of what's called enumerative geometry, enumerative being counting. We don't ask questions like how many lines are there through 1 point where we can't count, but we ask questions where we can count. And there's a general theorem called Bezout's theorem, which says that if we have something of degree m and something of degree n, that those curves intersect in mn points if we know how to count carefully. Okay, so for example, 2 lines intersect in 1 point, that we've seen. 2 conics, conic means a degree 2 curve, like the 2 circles we looked at, those always intersect in 4 points. Okay, well, there's a unique line through 2 points, we saw that. And what about a conic? Well, if I specify 5 points, then there's a unique conic actually through 5 points. So if you think about a general quadratic equation, you'll see that the number of coefficients there is actually 6, but we can scale the equation, and we won't change the geometric picture. So there are actually 5 conics. Okay. And we could ask an equation about rational quartics. I'm not going to explain what rational quartics are. But anyway, if you specify 11 points, it turns out that if we take these points generically, there are 620 rational quartics through 11 points. I didn't emphasize, by the way, that we need generic things. For example, we don't want to intersect 2 lines which are the same line. Right? So we're allowed to sort of lump these things until they intersect generically. So for most curves, these statements are true. And this particular problem is one that the geometers of the 19th century who worked on these kinds of problems didn't solve. And quartic means degree 4. There's similar numbers for degree 5 and on up. That particular number and the ones for degree 5 and up were only calculated 5 years ago. So they're beyond the scope of this lecture because Hodge stops 50 years ago. But of course, I couldn't resist, as John said, mentioning that the ideas that come into geometry, I've emphasized so far the algebra, and here we see a glance of a different direction where new ideas are coming into geometry. The ideas to solve that problem came from a very different source. Okay, well now we need to go beyond 2 dimensions, I'm afraid, to get closer to the Hodge conjecture. So instead of the Euclidean 2-plane, we could, for example, look at 3 space. We already did. We looked at lines in 3-dimensional space, and you studied, when you studied geometry, solid geometry, part you didn't like, about tetrahedra and spheres and so on. Okay, and so similarly, we could take our evolved form of the Euclidean 2-plane, which is with complex numbers and points at infinity, and do that with 3-dimensional space. So we get CP3. Well, why stop at 3? Okay, so instead of having, just 3 or 4 numbers, we could have as many numbers as we want. So now to locate a point in this space, CPn, remember they're complex numbers, and so they're actually 2n real numbers. So this space looks like 2n dimensional space. It's quote-unquote ordinary 2n dimensional space, if you can picture that. All right, and so instead of points and curves, the curves we studied in the plane, we could look at higher dimensional cycles. So we could look at not only at points and curves, but in space we have surfaces, like the surface of a sphere. And so we could look at surfaces and higher dimensional things inside CPn. So what we call a shape that's algebraic, an algebraic cycle, is the solutions to a polynomial, is the set of solutions in that space, say CPn, to a bunch of polynomial equations, just as we wrote one polynomial equation in 2 variables to cut out a curve inside the plane. So we can write lots of polynomial equations to cut out lots of interesting shapes inside this high dimensional space. So you see that we can actually track that by studying algebra, because it's given by a finite set of data, just a finite number of polynomials, each one has a finite number of coefficients. So that's algebra. And we have to distinguish in there that some of these shapes we get are smooth. That's a new technical term, and some aren't. So what does smooth mean? Well, let's look at this example. So here we have two cubics. These are cubic polynomials. This one is y squared equals x cubed. I've drawn the graph. Here it's y equals x cubed. And we'll ask about smoothness at the indicated points. So what smooth means is that if we look closer and closer, the thing tends to look more and more flat. Here we have a curve. I've drawn it as a real curve. And what's a flat, real picture in one dimension? A flat, real picture is just a line. So something will be smooth if we look close enough, it looks like a line. So if we look a little closer here, well, that the first shape tends to look like this. The second shape, if we look, well, it's starting to flatten out a little bit, you see? And if we look a little bit closer, this one still has these two branches, whereas this one is, again, flattening out. And now this one, if we look very close, has almost flattened out, whereas this one still looks like that. And no matter how close we look, this thing is still going to look like that. It's not going to look like a line. It's somehow been folded up. So that point is not smooth, whereas that point is smooth. Okay? And so if we have a smooth shape inside CPN cut out by these polynomial equations, that has a special name. That's called a projective manifold. So it turns out that the kinds of spaces that we want to consider in the Hodge conjecture are exactly these. Smooth shapes we get by writing polynomial equations in CPN. So that's the arena for the Hodge conjecture. Instead of our space being CPN, we'll now look at this shape sitting inside CPN and forget about the rest of the points in CPN. So that new shape is going to be our ambient space, the space in which we're going to put other shapes. So instead of CPN, we have this projective manifold. Okay? We're not going to go any further. That's going to be the most complicated shape I'm going to tell you about. That's the most complicated space. So we forget about everything else, and we have this projective. Oh. Well, John said I was energetic. Okay. Well, maybe fully charged, but now it's decided to stop. Technology. Okay, so a projective manifold, again, is given by polynomial equations, which somehow are smooth. They have to satisfy that microscopic condition. And so here I'll call it X. That's my yellow space now. Before we had this nice simple plane, but now we have this high-dimensional complicated shape. But again, it's given by this nice algebraic data. We just have a bunch of polynomials, and we look at solutions to those polynomials all at once, simultaneous polynomials. And inside, we're going to put these algebraic cycles. So they might be points, they might be curves, they might be higher dimensional. So again, these pictures are merely schematics, right? And such a cycle C is given by, again, polynomial equations. So if we start out in our big space, our number space, so to speak, CPN, we first impose these polynomials. That gives us the big yellow space. And if we want shapes inside this, well, we just impose more equations. If we just impose these by themselves, we would get this shape in CPN. If we pose both simultaneously, we get these shapes inside of X, this projective manifold. So these are some of this is the space, certainly, that we're studying in the Hodge conjecture, this projective manifold, and these are some of the shapes inside of it. So the Hodge conjecture concerns algebraic cycles inside projective manifolds. Okay, so you see we've hit on three of the themes, namely geometry is the study of abstract space. Now our space is a projective manifold. We have distinguished shapes, and here the geometric point is that we have this algebra. So we can write down polynomials, solutions to polynomials. Those are particular shapes we study. And as you've seen, there's an interplay between geometry and algebra. So here's a rogues gallery of some of the characters that entered in the development since Euclid of those ideas. Maybe picked at random or because they had beautiful faces, I don't know. And, so if I'm going to go further and tell you more about the Hodge conjecture, what is the question about these algebraic cycles inside projective manifolds, then we need to introduce another theme, which is to bring in topology. So we need to introduce a new sort of shape to plunk inside our space. Okay, so here's topology. So let's start by going back to our Euclidean plane. We can breathe easy for a moment. And inside our Euclidean plane, well, we've already seen points. That was our first shape. We also saw lines, but now we're going to look at something different. The lines I looked at before went on forever. There were always lines that went out in both directions forever. Here I want to look at a line segment, just a little block like that. So here we have just a line segment. It only goes, for 4 centimeters or something. And here we have a new shape, which is a triangle. And here I don't mean the boundary of the triangle, 3 sticks put together, but rather all the interior, the shaded part in red. So it's so to speak, a solid triangle. Okay? Now, these basic shapes are what we call simplices. And if I hadn't stopped at the plane, you can imagine in 3 dimensions I would get the next shape. That one we could see. What would it be? It would actually be a tetrahedron, a pyramid. So if you imagine a pyramid, it looks like a triangle sitting on the floor, and then one more point up here, and I connect this point to all the points of the triangle, and that sweeps out some solid. That solid is a 3-dimensional simplex. Well, I just snuck in the word dimension, and each simplex has a dimension which tells us how big it is. So this point is 0-dimensional. This line segment or stick is 1-dimensional. That triangle is 2-dimensional. So again, if I want to use coordinates, for example, to tell you, then I could tell you how many numbers we need to navigate around that space. Or we could just count the vertices in the picture. Here there is 1 vertex. Here there are 2 vertices. Here there are 3 vertices. And the dimension is 1 less than the number of vertices. So these figures are actually very combinatorial, meaning, again, it's a finite amount of data. All I give you are the vertices and how it's hooked up. Well, these things have boundary. So, for example, the boundary of this triangle are these 3 sticks put together. Well, these sticks are 1-dimensional simplices. And so now we have a new type of shape, which is not a single 1-dimensional simplex, but a union of them. So that's what we call a chain in topology. Don't worry, there won't be a quiz on all these words. And if we take the boundary of this stick, well, that has 2 points. And if we take the boundary of the point, well, there is no boundary. There's nothing smaller. Okay, so it's an important technical point, which I won't emphasize, that these chains and cycles, they have a direction. So that's called an orientation. So for example, this stick, we have a preferred direction. We point that way or we point that way. And to orient the point, that's a plus or a minus sign. We could think of that as a sort of +1 or -1. So this orientation on points is just a sign like that. And now, if we put together a chain, we already saw one here. It's just a sum of these simplices. So here you see this figure building up. It's just a bunch of these sticks, building blocks. And each time I put it together, that boundary point disappears. One of the boundary points disappears because one of the pluses collided with one of the minuses, and they cancel, so to speak. So you see, we start to add these things and introduce some sort of algebraic structure on these kinds of shapes. Okay, and finally, what's called a cycle. That was the term I was using loosely before. Here, what it means is a shape like this with 0 boundary. So, for example, this triangle here, the boundary of this triangle, which looks like that, that has no boundary itself. And here we see an octagon, again with no boundary. Okay, so in topology, we have a very different picture of these cycles. They're just built out of these basic building blocks. Well, that's one kind of topology. And Poincaré, who I think was on the last slide, I didn't comment on him, he certainly, there was topology before Poincaré, but he started to put it together, certainly in a systematic theory. And what we want to do is look at these inside some more general shape like this. So this shape here, which is where we're going to look now at cycles instead of in the plane, this is the surface of what looks very much to me, since I missed dinner, like an egg bagel. So inside this bagel, we're going to put, it's just the surface, by the way, not the solid one, but just the 2-dimensional surface. Now, how can I think of this 2-dimensional surface? Well, one way I could think about getting that is to take a sheet of paper and, for example, if I wanted to get a cylinder, I could just roll it up like this, identify that. Well, imagine taking this sheet of paper, identifying the top and the bottom. That would give us a cylinder. Well, here what I've indicated actually is not only are the top and the bottom identified, but the middle line is meant to be identified with the top and the bottom. So it's as if I not only folded it once, but I actually folded it twice. So this thing would fold over itself twice. So if I just identified the top, the middle, and the bottom, these horizontal lines, I would get a shape like this. That's not yet the torus. What I should do to get the surface of the bagel is now identify the other way. Well, I can't with a sheet of paper, but topologists don't have paper. They have sheets of rubber. So with a sheet of rubber, I can stretch and make this shape. And again, I've indicated that in the vertical direction, I not only fold once, not twice, but actually 3 times. So that means that I folded this shape, this rectangle, 3 times in that direction, twice in that direction to get this torus. So that means that this one point on the torus is not only represented by the one point here, but actually by 6 points. So all those 6 points, if I roll them up, will actually map to the same point on that torus. Okay? So by introducing this auxiliary rectangle, we can navigate, so to speak, around the torus. And that's a way we can think about shapes in the torus. So now we can have lots of different cycles. And what's important when we take chains and cycles is that we take sums. So we already saw the sum when I built it up, the sum of plus and minuses, where the boundary was canceling. But now I'm going to allow more complicated numbers, 2/7 minus 1/3. Okay? So we can take sums with different kinds of numbers, depending on what number system we want. Here I've chosen to take rational numbers. So we'll consider 2/7 times this point plus 1 minus 1/3 times that point. So that's a sort of formal object, but that's the kind of object we want to consider in this kind of topology. So for example, we can take this line. I didn't attach a number. That will correspond to some curve on this torus. And the curve will look roughly like that. So this line winds 3 times in that direction, twice in that direction. And when it comes back to the vertex, it comes back to the same point. So whereas this line segment has a boundary here, it actually has no boundary here. It's actually a cycle, because the 2 boundary points here correspond to the same point on that torus. Okay, well, here we could take one of our old friends, just a triangle here. That will correspond to some jagged shape in the surface of this torus. So you should picture these cycles as being sort of jagged objects inside this space. Okay, there's one important notion that we need, which is we want to not differentiate between certain of these cycles. So here we have this red cycle here at this boundary. We have the red cycle at the other boundary. And what I want to say is that those cycles are equivalent. They're certainly not the same. They're different shapes. But you see, they bound something in here. So really, they're counted with signs. The orientation enters. But the idea is that they occur as the boundary of something higher dimensional. That higher dimensional thing is not a cycle. It has a boundary. Being a cycle meant no boundary. But that's what we mean by an equivalence. And we introduce a long word called homologous if their difference is a boundary. Here you see another example. We only see one boundary component. So what am I saying this is equivalent to? Well, it's equivalent to 0. It's equivalent to 0 because it's a boundary. So remember, we're allowed to consider shapes with numbers, and 0 is perfectly good. So 0 is some kind of non-shape there. And this shape is equivalent to 0. It's a boundary. And so if we consider these classes where we identify them, that's what up to equivalence means. It means we can't distinguish ones where the difference bounds like that. Then that's what we call a class of cycles, and that class is called a homology class. So the reason for introducing all that is that it's very computable. Once you allow yourself that, then you can start chopping your space. There's a variety of techniques, and you can start computing these sorts of cycles. Okay. We can also do our game of intersecting. Just as we did with these nice algebraic equations, we can also intersect these sorts of cycles. And what happens when I intersect? Well, here's where the orientation, the signs come in. So for example, this green curve and this red curve, they intersect at a point here. But if I just deform this red curve a little bit, I just take my finger and lift it up here, then all of a sudden it intersects in 3 points. And so it looks from that picture as if I've changed how many intersection points there are. But the point is that we have these things called orientations which come in to give signs. And so if I count how many intersections there are, and I count plus, minus, plus, then I still have 1 point here. The plus and the minus cancel, leaving me the same picture as there. And so there's an intersection theory for these cycles, just as there are solving simultaneous equations. So we have this sort of intersection number. So here's a challenge for you. Here you see a green curve, which just goes around the torus once. That's this green curve. And now we see the fellow we saw before, this red curve, which goes around like that. And the question is, how many times does that red curve intersect that green curve? I'll give you a hint. The signs are all plus. Well, if I bring in some guidelines, you see, now I have 6 sticks, but those 6 sticks all correspond to this. So really, we only have that one shape here, but we have 6 sort of shadows of it, and you see that it intersects 3 times. So those curves actually intersect 3 times. Okay. Well, the fellow who really developed this intersection theory, and much of the topology following Poincaré, is Solomon Lefschetz. And he's rather an amazing figure in this story of Hodge, and he's certainly the direct predecessor, I suppose, in many of these ideas to Hodge, as we'll see. So we're getting close. But don't give up yet, because we still have more things to go. Okay, so he developed these topological tools, and now he applied them to the shapes which are projective manifolds. So you might recall that this torus we've been playing with here is actually a projective manifold, because I said it was the shape of the set of solutions to a cubic equation in the plane, in the complex plane. So we really get a torus, and we could study those. Okay. Well, it turns out that when we play with these algebraic cycles, for example, we have a degree. That degree is the degree of the equation that I use. So here, I'm taking, again, our friend the plane, imposing one equation, and we get a curve. That has a degree. And I said that that degree could be computed by intersecting with a line and counting how many intersection points. So that was something we did by solving polynomial equations. And what was realized with these topological ideas is that that's actually a topological invariant. In other words, if I deform this curve a little bit, just as I did before by lifting that red curve over here and just deform it, it won't anymore solve a polynomial equation, but it will still have a degree and an intersection number, and that intersection number won't change. And so that's a very powerful idea, because instead of being in this rigid realm of these polynomial equations, you can now start to deform things in this very fluid realm of topology. And so that's very important computationally to be able to do that. The theorem that says that if we have a curve of degree n and a curve of degree m, they intersect in the product of the degrees, that many points, that theorem is also topological about these intersection numbers. And it turns out that a lot of theory of surfaces, which was developed in the 19th century, that the invariants there also turn out to be topological. So it was a very powerful idea to introduce this kind of topology into the study of those spaces, which previously belonged just to the realm of algebra. So you see geometry reaching out in very different directions. On the one hand, to algebra, spaces defined by algebra. On the other hand, looking into topology, where we have a much worse vision. We can't distinguish things which are moving like that, but somehow we didn't have to. Okay. So finally, I can tell you the Hodge conjecture, not as a conjecture, but as a problem. So there's a natural question, which is to start with a projective manifold, here called X. And let's start with this broader class of shapes, these topological cycles. We might have these triangles, very jagged shapes. And what we can ask is it somehow possible to define that shape by a polynomial equation? Well, certainly we can't define exactly that shape by a polynomial equation. But remember, we're not distinguishing those shapes when they deform a little bit, or if their difference is a boundary. And so what we want to ask is, if we allow it to deform, can we deform it in that way to an algebraic cycle, to something defined by polynomials? So that's the question that the Hodge conjecture addresses. Whether these topological cycles inside this particular space can be made algebraic. Well, there is one obvious condition, which is that, remember, an algebraic thing is defined by complex equations. And so that means it has to have an even dimension. You remember our curves, which are complex, really look like surfaces. They have dimension 2. In the next dimension, we would have 2 complex numbers to navigate, and so that would look like real dimension 4. So we better have that our shapes have even dimension. That's certainly one condition. We couldn't hope to describe them by complex numbers otherwise. But the question is, are there other conditions? Well, this is a sort of typical question in geometry, where we have some topological class. Here we have these topological cycles, these jagged shapes, and we want to find some nice geometric representative. So that really covers a lot of problems in modern geometry, where you want to find some sort of particular geometric representative. And this is one example of that sort of problem. Now, Hodge made a proposal, that's his conjecture, for what the condition is on a topological cycle class to be algebraic. And to explain what his condition is, I have to bring in this final dreaded theme, which is calculus. So since the level of material goes up, I'm allowed to go faster. Okay. Well, the first slide, you can still pay attention if you don't know calculus, because we're back to Euclidean geometry. And so here we're going to be in Euclidean geometry, and we're going to discuss an aspect we haven't seen before, which is measurement. So we really measured angles before, but now we're going to see it in spades. We're going to measure lengths, we're going to measure areas, and we're going to measure volumes. So the basic kind of measurement is really lengths and angles. And once we know about lengths and angles, then there's a nice formula in terms of these lengths and that angle that tells us the area. And similarly, we can compute this volume in terms of lengths and angles. So the kinds of measurements, the fundamental ones, are lengths and angles, and from that we can compute everything else. So here are some basic shapes. This is just a line segment. That's a parallelogram. That's called a parallelepiped. And how we can describe these shapes is just in terms of these vectors. So you see that vector, well, that's by itself. This vector somehow sweeps out this parallelogram, and those three sweep out that parallelepiped. So again, these kinds of shapes are described by a very finite amount of data, these vectors. And let's introduce a little bit of notation. So the v's, v1, here we have 2 vectors, here we have 3, v1, v2, v3. Those will describe our shape, and we'll call L, A, and V the length, the area, and the volume. So this is the length of that vector, the area of the parallelogram, and so on. And now an important point is what happens when we scale. So let's take a number which is positive, and let's replace each vector by that number r times the vector. So the red vectors, for example, are 1/2 times the blue vectors. Well, what happens to length, area, and volume? Well, the length cuts in half. The length multiplies by r. So I went from the blue to the red by multiplying by 1/2, dividing by 2, and similarly, the length divided by 2. What happens to the area? Well, the area divides by 4, which is r squared. And the volume, well, it multiplies by 1/8, which is r cubed. Okay? So actually, the dimension of this figure is related to this scaling, when we just scale by stretching, this dilation. Well, in complex geometry, you have to remember now that these vectors, which are just displacements between points, the points were described by complex numbers, and so are these vectors. Well, we can now multiply not just by a real number, but also by a complex number. And so here I've represented a complex number in a different way, again in terms of two real numbers, r and theta, but r is this r that we saw before, this positive scaling, and theta now is an angle. And so multiplication by theta is really a rotation. So we can scale by rotating, and what happens to these measurements when we rotate? Well, exactly nothing. Measurements are invariant under rotation, length, area. If I just take a figure and rotate it, I don't change. That's somehow the key point of what Hodge proposed. So it's right here in terms of rotation. Well, now we have to get into calculus. So what is calculus? We have to compute areas and volumes and so on, lengths, by integrating, but we want to compute lengths and integrals over curve shapes. So how do we do that? Well, we approximate them by these straight shapes. So here we took a curve, approximate it by these straight shapes, these vectors. Here we take some surface, imagine that to be a piece of a curved surface, and we approximate by these nice parallelograms. So they're based at these particular points. So what we'd like to do is add up not the area of these, but we'd like something that gives us a number at each point and tells us really a factor by which we scale things. So what are the kinds of things we can integrate? You see, I can say that this parallelogram has a certain area, but I don't really have a standard of measurement. So what I have to do is give myself something which will measure the area of that rectangle. So the kinds of things that I might approximate, what kind of information would I have at each point, is something which, given two vectors, gives me an area. Well, that's something that's called a differential form. And so the kinds of things that we integrate when we have these curved things, as you see, I've just described it, are differential forms. So they exactly tell us lengths and areas and so on. And so these were studied by Elie Cartan, who figures quite a bit in this sort of geometry. And the main properties, I'll just tell you very quickly. One is that we can tell the degree of the form. So here we have something of dimension 1, and so we need something pertaining to length. So that we call degree 1, because it's dimension 1 that has length. Here we need a degree 2 form, that's something pertaining to area. And that was determined by this scaling. Okay? And we also have, well, this change of variables formula. That's just a way of telling you that what I defined, I could tell you in pictures. And then we have the Stokes theorem. That's an important theorem, which I won't try to explain. But you'll see that if we integrate over this red surface, we have a boundary, which is this green one-dimensional shape. And the integral over that boundary, as opposed to over C, is related on the other side in these differential forms by differentiating. So this is an equation that relates differentiation to a boundary. So you all know the version of that, which is in one dimension called the fundamental theorem of calculus. This is a higher dimensional version, but it tells you that differentiation is somehow analogous to this boundary operator. Well, that idea was taken up by de Rham, and he did it took that idea to the max, so to speak. And so what he found was that he could use this differentiation to define a notion of chain and cycle on these objects that we integrate. And other objects and ideas in topology, like intersection numbers, actually could be expressed in this language of calculus. So for example, in here, where we had this intersection number before we computed to be 3, it turns out we can represent this green curve by differential form, which is just called dx, and that the intersection number with c is obtained by integrating dx over c. Well, the integral of dx is just telling us the displacement in x as I traverse c. X, whoops, I forgot to draw. X is this way, y is that way. And so here we started, and you see by the time we get to the end of c, x has increased 3 units. And so that integral comes out to be 3. And if I perturb c a little bit, just move it a little bit in the middle, that integral will still be 3. And so that integral is actually a topological invariant measuring intersection number. Well, on smooth spaces, like this projective manifolds, we can relate these kinds of differential forms up to this sort of equivalence given by this boundary operator to topological cycles with the equivalence given by the topological boundary we had before. That's one of de Rhom's contributions. So we see another theme, which is very important in geometry, that we have these local objects, these things in calculus. They're just functions, things we know at every point, and they can tell us information like intersection numbers. Well, in complex geometry, there's a whole line of development that leads directly to Hodge's conjecture, and that's something I don't have time to tell you about. And there are a few names that should be there, for example, Gauss and Jacobi. And what they studied, so to speak, are undoable integrals in calculus. So if you took or taught calculus recently, which I've done neither, so if you integrate something like the 1 over the square root of a quadratic function, like 1 over the square root of 1 minus x squared, then you'll find you get things like trigonometric, actually inverse trigonometric functions. And if you then ask the question, how do I integrate 1 over the square root of a cubic function? Well, you find that you can't do it with our arsenal of elementary functions. So there were new functions studied, and Riemann is the one who took this idea, and really his contribution cannot be overestimated. But since I don't have time to tell you about it, at least next week you can come and hear a completely different aspect of Riemann's work. Okay. And instead of one-dimensional integrals, we could study two-dimensional integrals. That's what this fellow did. One of my younger colleagues looked at that picture and said he would be really a terror to have as a thesis advisor. I couldn't say. And here we see our old friend Lefschetz, who took these developments of Picard and Riemann and saw how topology applied, and not only to double integrals, but integrals much higher. So again, these topological ideas play a key role. Certainly Riemann introduced them, but Picard used those ideas, and Lefschetz developed not only used them, but developed the topological ideas. So he's a sort of towering figure in both topology and algebraic geometry of that side. Okay, so finally we're ready then to talk about Hodge. And Hodge, what he did was introduce, again, this idea of calculus in a place where it hadn't been before, so to speak, which is on these algebraic manifolds defined by polynomial equations. And he looked at, but before he did that, he looked at spaces where we have measurements, sort of generalized notion, not just the Euclidean space, and he picked out very beautiful differential forms called harmonic differential forms. And again, we see a glimpse of other places where geometry reaches out, and here the interaction is with partial differential equations, the sort of equations you heard about in the last lecture, but really the particular equation is the one you heard about in the lecture on Yang-Mills, an equation coming from electrostatics. Well, again, this harmonic differential form is an example of this sort of problem that I said before, and it's had a great influence. And what he did was to use this idea that on a projective manifold there's a natural notion of measurement, of distance and angle. And so he was able to apply his theory of harmonic forms there. And in that way, he was able to recover, really, the results that Lefschetz made, who made amazing results there. But also, he's able, because he's on this complex thing, he's able to introduce this idea of rotation number. So now that we're on a complex space, we could also rotate by multiplying by e to the I theta. And so differential forms get a new structure, which is this rotation number. And amazingly, he saw that that rotation number really introduced a structure not just on these differential forms, but actually on the topology that they represent by de Rhom's contribution. So suddenly there was a new structure on the cohomology, on the homology groups of this manifold, what we could think of as a rotation number. Okay. And these algebraic cycles, finally, if I integrate over those, well, we're adding up volumes over these complex spaces. And remember, the volumes that we get are invariant under rotation. So the kinds of differential forms that pertain to those have to have zero rotation number. And that means that these have, inside this homology, they're very special. They have zero rotation number. Okay, so finally we can state the Hodge conjecture. As I said, that was stated in 1950 as part of his address to the International Congress. Here you see the beginning of his proceedings, where he talks definitely about the topology and the interaction with these spaces of algebra. And here it is. So we have our space, which is this projective manifold, and inside we have two kinds of shapes. One are these topological cycles, these sort of jagged things in purple, and then we have these nice ones described by polynomial equations. And the question is to know when these can be deformed, allowing to go over cycles, chains deformed through a boundary, to become here. Okay. And the conjecture is that this kind of cycle, where Hodge introduced this rotation number, is equivalent to something algebraic exactly when it has rotation number 0. So it's easy to see that that's a sufficient condition, and the conjecture is that that's a necessary condition. The conjecture is that that's actually a sufficient condition. Okay? And notice we have here, we're allowed these numbers. We can't really ask the question on the nose for a single shape and deform to a single shape. We have to ask the question for these numbers. And in fact, the numbers I've used are fractions. They're rational numbers. And one of the discoveries, not too long after, is that the conjecture is false if we use only integers. So let me quickly say some things about some progress and related items to this conjecture. That is the Hodge conjecture. It's unsolved as of this moment. That's why there's $1 million bounty on it. That's why it's identified as one of the 7 great failures of the 20th century. But there is some progress. So Lefschetz, again, in 1923, he proved the conjecture where we take our big space and we have a cycle that's almost as big as the space. Namely, we're in a space that's described by 2n real numbers, or n complex numbers, and here we have something described by n minus 1 complex numbers. And for that case, the conjecture is true. Okay. Lefschetz also showed that if you show it for these large shapes, large dimensional shapes, then there's an analogous smaller dimension, complementary, so to speak, for which it's true. So for example, in 3 dimensions, 3 complex dimensions now, I'll speak in terms of complex dimensions, if we know it for 2, which we know by the first line, then the second line tells it for 1. So in a 3-dimensional shape, 3-dimensional projective manifold, we know it always. And so the first case where it's interesting is in real dimension 8, or complex dimension 4.
What is the negative cycle? You got p greater than n?
Oh, well, it's a mistake. Well, it should have been greater than n over 2. Sorry. Okay. So the Hodge conjecture has been verified for special examples in the dimension where it's the first case, but really only for special examples. On the other hand, one reason to believe it is that you can say, suppose Hodge is true, then we know such and such. Well, sometimes such and such has actually been proved by other methods. So that's a little piece of evidence towards the conjecture. Well, it also fits into a larger circle of ideas, and that's another reason to believe it. So Grothendieck, who developed algebraic geometry in other directions, it fits in those directions, which are really more arithmetic. And again, in arithmetic, there are analogous conjectures, like the Tate conjectures in number theory, which are analogs of the Hodge conjecture. And so the Hodge conjecture fits into a much bigger circle of ideas. You'll recognize, incidentally, the Tate there as our host. Well, I didn't know how he'd introduce me. So. All right. Well, finally, we should ask, is the Hodge conjecture true? And, well, I consulted with a bunch of experts, and I must say that I didn't get any ringing endorsements, yes, although after a long pause, they all answered they thought it was true. Well, there was a paper published in 1969, Hodge's general conjecture is false for trivial reasons. Well, that title was really a joke, because Hodge, the general conjecture, is something else than I've said. And actually, this particular author, Grothendieck, again, had nothing to say about the conjecture that we call the Hodge conjecture here. And in fact, what he says about that is it's plausible enough, but as long as it's not disproved, it should be regarded as a central problem. But of course, he gives that caveat, and it indicates that maybe he thought it wasn't true. And here's a fellow who definitely thought it wasn't true. And what he says is that the question posed by the conjecture of Hodge is natural enough. But unfortunately, despite the word conjecture that's attached to it, there's not, as far as I know, a shadow of a reason to believe it. Okay? And he says we would do a great service to geometers if we could dispose of the question by means of a counterexample. So he seems to indicate that maybe it's not true. And it's rather amazing to think not only about the Hodge conjecture, but about the other conjectures that we have that, at the time that he made it, there was really very little reason probably to believe it. I mean, it fit into a natural set of developments, but he probably didn't have so much evidence. And it's really a tribute to Hodges and the other characters we're hearing about, to their intuition that they put their finger on these central problems which have survived. But I'll give the last word anyway to André Weil, who wasn't so thrilled with this use of conjecture and people conjecturing so quickly. So he says that, well, when you're working on a math problem, it would be great you find out if such and such would be true, and you might try it, and maybe you'll prove it's true right away. Maybe you'll realize it's not true, and you'll go on from there. But if it resists your effort, then you call it a conjecture. And there's a lot of examples of that. And, well, he recommends against that. Okay, thank you.
Thank you, Dan. Now I understand how you can do it. Anyway, are there questions?
Before the test. Yes?
Do you get $1 million if you disprove it?
Yes, I think so. Well,
I'm not sure. I'm sure you'd get something. But no, that question, the same question applies to the Riemann hypothesis. And I think the, do you know? I mean, I think on the website, I think the official thing is to prove it. But I'm sure you'd get a substantial, if not the whole thing, if you settle it.
well, if you're a
one way.
graduate student and you disprove it, you'll get a very good job. Let's put it that way.
Well, that's, in any case, yeah, that goes for
For all the problems.
for all of them. Yeah.
Say a little bit more about what the rotation number of
What is
An hour
the
later.
what is the rotation number of a?
What is the rotation number of a form? You want to hear more about that? Well, so a differential form, as I said, it's if it has degree k, the input are k vectors. Okay, and we know they were k vectors because what it gives is as an input k vectors, an output a real number. And if I scale all these by multiplying by a positive constant like 2, then that number will multiply by 2 to the k. That's what told us it was degree k. Well, now imagine we're in this complex world, and we're allowed that our inputs are complex numbers. So now what we're allowed to do is rotate all of these numbers by an angle, e to the I theta. Well, now this form will, in general, multiply by e to the I something times theta. So in other words, if I rotate each of the... so first of all, the inputs are now complex vectors, and the output's a complex vector. A complex vector is a vector in the plane. And if I rotate each of these inputs by an angle theta, then in general, this output will multiply by some number s times theta. That number s is the rotation number. So if s is 0, zero rotation number, it means that this is invariant. And so if this form is representing volume, then it has to have 0 rotation number.
Yeah, back there.
Could you give any sort of explanation, like what a number theory analog to Hodge conjecture would look like?
No, but John can.
It's hard to imagine how number theory could be related.
The question was, how do you explain what a number theory analog of the Hodge conjecture is?
I think it's time for some refreshments. Let's thank the speaker again. One more week.